Hi guys, welcome back to my channel Pirai Academy. In the series of data structure playlist, today we are going to see about binary search tree implementation. Okay, in previous video we have already saw about the traversing techniques in binary tree, right? I want you to understand those traversing techniques, okay, so that it will be quite helpful in the binary search tree implementation. Like you want to know about recursion, okay, how recursion tree and recursion stack work, okay, then you want to know about recursion stack. So this is enough for binary search tree. And if you want to implement a BFS traverser in a binary search tree, it is not recommended, but still if you want, then you want to know about queue data structure, okay. For my video you want to know about these two things, or if you only want to know about this recursion, that's enough, okay, fine. Now what are all those ADTs we are just covering in this video? Are inserting into a binary search tree, deleting a node in a binary search tree, searching a node in binary search tree, and min and max value in a binary search tree, and traversing the binary search tree, okay, mainly in order traversal, because I have told you the property of the binary search tree in a types of trees, right? When we are doing a in order traversal in a binary search tree, then it will be giving me a sorted order, okay. And also I told you why we are going from binary tree to binary search tree, because we are just maintaining them in a sorted order. That's the use of binary search tree, okay, fine. So let's get started. So see here are some operations. Now we are just going to construct a binary search tree using these operations, fine. Now insert 6, which means it is going to be a root node, okay. Like binary search tree also have three attributes. One is left address, next one is right address, mean right child address and left child address, and its own value, which means a root value, okay, fine. Let's get started. So understanding this, also you must understand the property like all the left subtree values of this root should be less than the root value, and all the values in the right subtree should be greater than the root's values. That you have already know when I taught in the types of tree itself, right? Now let's get started. So first of all, insert 6, right? So I'll be creating a new node. So this is a new node, and its left child is null and its right child is null as of now, and its value is 6, and this is going to be the root. So we can do this in a constructor itself, okay. I'll be telling this in a code implementation, okay, fine. Now insert of 10, okay. So I'll be creating a new node. And first of all I will be creating a new node, okay. Then I will be telling you the logic behind it, okay. I have successfully created a new node. Now where should I insert it? Because in binary tree we have no conditions, we can do anywhere, right? But in binary search tree we have some set of conditions, right? So I'll be traversing from root, and check whether root value is what? Root value is 6. Okay. So the newly we are going to insert an element called what? 10 is greater than 6. So where should I insert it? I should insert in the right side. Okay, let me check whether the right child is null. Yes, it is null. Then for example, if its address is 200, then change its right child address as 200, so that there will be a linkage like this. Can you understand this? Yes. Now insert element called 6. Okay, again create a new node. Let me create a new node, and its left child is null and its value is 7, and its right child is null, okay. Now where should I insert it? For example, its address is 300. Where should I insert it? First of all, I will be checking for the root. So root value is 6. Whether 7 is greater than 6? Yes, 7 is greater than 6. Then I want to go to the right subtree. I must make this 7 in my right subtree. Whether my right child is null? No. Then go to my right child, okay. So I am going to the right child. So right child is 10. So 10 is greater than 7, which means 7 should be in the left subtree of the 10. Can you understand this? Yes. So whether its left child is empty, yes, it is null. So what are you thinking for? Just update the value. Just do this like 300 and connect them. That's it. Okay, fine. The next one, insert of 5. Okay, so I'll be creating a new node called 5, and here null and here also null. Okay, now let me take the addresses 400. Fine. Now I'll be checking from the root. What is the root value? It is 6. So 5 is less than 6, which means 5 should be in the left subtree of 6. Whether my left child of the root value is null? Yes, yes. So just update it. Just update it and connect them. That's it. Yes. Now the next thing, insert of 2. So now I'm going to inserting it. So let me create a new node called 2. I'll be let me create here 2 null and null. Okay. Let us take this address as 500. Now where should I insert it? First of all, root value is 6. Whether 2 is less than 6? Yes, yes. Then I want to check for the left child. What is the left child? It is 400. It is 400. So it is not empty. It is not null. So I want to go to the left child. Okay, go to the left child. Now 5 is greater than 2, which means 2 is less than 5, right? So 2 should be inserted to the left subtree. Left subtree. So I want to check whether my left child is empty first, right? Yes, it is empty. So just make this as 500 so that there is a linkage like this. Okay. Now the next thing is insert of 3. So I'll be just taking a new node, creating a new node, null and null. Okay. Take for example the address is 600. Now first of all I want to check for the root, right? Root. Now what is the root value? It is 6. Whether 3 is less than 6? Yes, yes. Then I want to go for the left child. Okay, left child is 400, so I cannot insert it. So go to its left child. So 5 is greater than the 3, which means 3 should be in the left subtree, right? First I want to check for its left child. Left child is 500, which is not null. So I want to go to its left child. So I will be now here at this particular node, right? Now its value is 2. So 2 is less than 3, which means 3 should be to the 2's right child. Right subtree. It may be child or maybe in a subtree part. Okay. So I want to check whether its child is null. Right child is null. Yes, yes. So this is my turn to change it. Change it to 600 so that I'll be having a connection like this. Okay. Now the next thing, insert of 1. Okay. Now I'll be creating a new node called 1 null null. Okay. Take for example its address is 700. Okay. Now I'll be checking the root value. It is 6. 6 is greater than 1. So I'll be going to the left child. Okay. Now 5 is also greater than 1. So go to the left child. 2 is also greater than 1. So what is its left child? It is null. So make this as 700. That's it. Now we have successfully inserted 1. Now what is the next operation? It is search of 5. Okay. In binary tree we used either in order or pre-order or post order or level order traversal, right? But in binary search tree we are not going to use those things. We are just going to use the range kind of view. Like take for example, here it is what? 5. I want to search for 5, right? So initially I will be at the root. Okay. Let me take any other color. So here, right? So here it is 6. Okay. Whether 6 is greater than 5? Yes. Yes. So that I can say we don't want to go to its right side. Its right subtree definitely don't have the value as 5 because everything will be greater than 6, right? Then I can eliminate them. Now go to its left child. Left subtree. Okay. Left subtree. So go here. It is what? 5. So I have found out 5. So I just returning it. Can I understand this? So if it is like any other value, you will be neglecting one side and going to the next side. Either you can neglect the left subtree and go to the right subtree, or neglect the right subtree, go to the left subtree. So it is kind of like binary search, right? So that's the reason why when I am teaching you the types of types of trees, that's why I have told you that binary search tree is kind of discovered or inverted to just search the values efficiently, but it has some drawbacks also. I'll be telling the drawbacks also. I already told you. Still, I will be again telling you the drawbacks. As of now, just continue this. Okay. Now, what's the next thing? It is search of 4. Now, see here. I am particularly here, right? Whether 6 is greater than 4. Yes. Then I should not go to the right side. I will be going to the left subtree. Okay. Go to the left subtree. Now I am here. Whether 5 is greater than 4. Yes. Then I don't want to go to the right subtree. Go to the left subtree. Okay. Go to this 2. Now for this 2 also, whether 4 is greater than, yes, 4 is greater, which means I want to go to the right subtree, not to the left subtree, right? So go to the right subtree. Now I am here. 3 is less than 4, which means I want to go to the right subtree. So go to the right subtree. Now right subtree is what? Null, which means here I can say surely 4 is not present. Can you understand this? So in this case, I'll be returning false. Now delete of 5. So deletion in binary search tree is also quite difficult. Okay. So before going for the deletion, first we can see about the how to find the minimum and maximum value in the binary tree. Okay. If I am giving you to find what is a minimum value and what is a maximum value in the binary tree, I'll be teaching that first so that we can go for the deletion. Okay. So if I tell you want to find the minimum value in a binary tree, then don't worry, its leftmost node will be the minimum node. I already told you in the property itself, right? So I'll be standing here. Okay, whether it is a leftmost node, no, because it has a left child. Okay, then go there, go to the left child. Whether it is a leftmost node, no, because it also have a left child. Okay, go to its left child. Whether this node is a leftmost node, no, it has left child as 700. Okay, go to the 700. Whether this is a leftmost node, yes, it has null. Okay, then one should be my answer. Can you understand this? Okay, so this is how we will be finding the minimum. If I tell you to find maximum, then you will be starting from here 6. Okay, whether its right child is null, no, then go to its right child. Okay, whether its right child is null, yes, then 10 is the maximum in among this binary search tree. So here output is 10, here output is 1. Can you understand this? Yes. Okay, so this is the basic. Okay, we can easily implement the minimum and maximum. If I tell you like take for example, if I tell you like for this 10, what is the minimum? From this 10, what is the minimum? Means 7 is the minimum. Okay, because these are the subtrees we want to find out the minimum. Okay, so in this case 7 will be the minimum. Now let's get into the deletion so that you can understand this clearly. Okay, so here delete of 5, right? So I'll be starting from here. Okay, now whether the 6 is greater than 5, yes, so I want to go to the left subtree. So go here. Now whether this 5 is equal to 5, yes. At this particular point, what I'm going to do is I want to check whether it has 0 or 1 or 2 child. As you know, in binary search tree we have a child range from 0 to 2. Yes. Now whether it has 0 or 1 or 2 child, it has only 1 child. Okay, then no problem. We can cut this off and make a link like this. Can you understand this? Yes. So it is basically like I will be just deleting. Now you don't want to understand how we are going to delete it. Okay, when I am showing the code, you can understand this. It is going to be a recursion code, right? So I'll be deleting this. Okay, and making the address here as 500. Okay, and I'll be joining this. That's it. So there will be a link, right? So like this. That's it. Can you understand this? So for deletion we have 3 types. One is if the node to be deleted have 0 child, if the node to be deleted have 1 child, if the node to be deleted have 2 child. Now we have successfully saw about the 1 child. 1 child means don't worry, just return the that one child which is available. If we have left child, then make the address as the left child. If we have only the right child, make the address as right child. That's it. Okay. If it is 0 child, then delete that node as it is, because 0 child means it is a leaf node. For example, if I want to delete 7, I can directly delete it. I don't want to do anything. I make here as null. That's it. Can you understand this? So basically, if we have 0 or 1 child, it will be so simple. If we have 2 child, then there will be headache. Okay, I'll be telling that also. See here, next operation. Let us continue here. Insert 12. Where I will be inserting the 12? I'll be just checking here. Here is 6. So 6 is less than 12. So I want to go to the right subtree. Okay, 10. 10 is also less than 12. So go to the right subtree. So the right child is null. Okay, then this is the point to insert 12. Null and null. Take for example, its value is 1000. Now here it will be updated as 1000. This will be connected here. That's it. Okay. Now what's the next value? It is insert of 11. So it will be obviously inserted where? It will be obviously inserted here. Okay. So let us take this as 1200. So here it will be updated as 1200. Null 11. That's it. Okay. Now here comes a link. Now the next value is 13. For 13, as you know, we will be having right child of 12. Okay. I just imagine like you already know about the insertion, because I done as many insertions, right? So that's the reason why I'm going fast. So here comes null, and let us take this as 1300. Okay, then here it will be updated as 1300, and the linkage will be created between them. That's it. Okay, so its right side going to be like this. Okay, now comes the important thing. So see here, delete of 10. Okay, we are going to delete 10, which means we are going to delete this particular node. Okay, as of now, how my tree is looking like? 6, its left child is 2, its left child is 1, and 2's right child is 3. Okay, here its left child is 10, and its right child is 10, and 10's left child is 7. Then here comes 12, and 12's left and right going to be 11 and 13, like this. Now if I delete this 10, what should be here? Because 10 has 2 children, right? So which should be occupied here? You can do this in two ways. In your left subtree, observe this carefully. In your left subtree of this 10, you can take the maximum value, or in the right subtree, you can take the minimum value. Like you can either take this 7 or take this 11 and replace in the place of 10. Can you understand this? Yes. So if I am going for the left subtree, then I want to take the maximum value. What is the maximum value in the left subtree? It is 7. Okay, then I will be just making this 10 as 7 and delete this 7. That's it. So my binary search tree will be looking like this. Or else you can also go like take this 10 instead, make this as 11 and delete this 11. That's it. You may also ask what we will be doing if again here we have like here we have 8 and or 8 or something like 9, and here comes 8, like this. If we are having like this, then what we are going to do? You may ask, or let me take some value like 9.5, not a float value, but still for the understanding I'm taking this as 9.45. okay, so see here, now if it is like this, then you may ask what I am going to do now if I want to delete the 10. Okay, what is the largest value in my right subtree? It is going to be 9.5. If I just delete this and make here as 9.5, then that's it. This is going to be the answer. You may also think, if there is no 9.5, then what should I do? I'll be just replacing this as 9, because the maximum value to its left subtree is going to be 9. Okay, I'll be replacing this 10 as 9. Okay, and I'll be deleting this 9. Deleting this 9 means instead of this 9, I will be replacing this 8. So it is going to be the recursion call. When we are going to the code, it will be more simple. Okay, I will be showing there. Okay, now this is going to the logic. Okay, similarly, we are going to do here. I will be starting from the root. Whether the 6 is equal to 10, no. Then go to the right child. Because 6 is less than 10. That's the reason I am going to the right side. Okay, here comes 10. Here comes 10. 10 means what should I do? I'll be going to delete it. So for deleting it, I can either go to the right subtree. Listen this, right subtree and take the minimum value, or go to the left subtree and take the maximum value. Why we are going to do this? Because many of them know how we are going to do this, but don't know why we are doing this. Because when we are going to the right subtree and taking the minimum value, it will be the immediate next value of the current node, the node that's going to be deleted. Okay, if we are going to the left subtree and taking the maximum value, then it is going to be the immediate previous value of the node that to be deleted. Now hope you understand why we are doing this. Okay, because I saw many of them just doing like by memorizing it, but I want you to understand this clearly. Okay, fine, let's get started. So see here I have got the 10. So I am going to the left subtree here and going to find the maximum. As you know already, yes, we are going to find the maximum. Already I have given you the maximum code right here, the maximum code. You can also do like this, or you can either go to the right child. So I am going to the right subtree. Now let me discuss with the right subtree. Okay, right subtree and taking the minimum value. So for the minimum also we will be having a function. Just call a function from this. So minimum means what? I will be checking for this 12 whether it has a left child. Yes, it has a left child. Then this is not the minimum. So go to the left child. Whether it has a minimum? No, because see here, whether it has a left child? No, because it has a null in the left child. Okay, that means it is going to be a minimum among this. So instead of 10, just replace 11. Okay, again delete this particular node. Just delete it, which means just make this as null. That's it. Now my binary search tree looks like something like, see here, these are removed, this is removed. So here comes 11. Okay, now see here, for 6 my right subtree is greater than that and my left subtree is less than that, and for the 11 also my left subtree is less than that and right subtree is greater than 11, and for 12 my left subtree is nothing and my right subtree is greater than 13. Correct. This is going to be the condition of binary search tree, right? So this is the overall logic part, and in coding part you can clearly understand all the logics. Okay, now just see here, what is the time complexity for insertion? It will be time complexity of O of n. You may argue we are just getting a log n. No, because sometime in binary search tree we may have a skew tree like this. For example, here 11, 12, 13, 14, 15. If you are inserting in this fashion 11, 12, 13, 14, 15, then my binary search tree is not balanced. Okay, so this is the disadvantage of using the binary search tree. Okay, so in this particular scenario, my insertion will be of O of n, because this is a binary search tree, and if I want to insert 16 or greater than 15, any value that is greater than 15, then it is going to take O of n. That's the reason why insertion is going to be O of n. Okay, deletion is also taking O of n. Okay, see here, if I want to delete this 15, I want to traverse n times. Okay, that's the reason why. Now searching also time complexity will be O of n, and maximum minimum also time complexity will be O of n. These all the worst case in case of skew tree. Okay, and for traversal, I already taught you the in order traversal, right? Whenever we are doing a in order traversal, we will be getting a sorted order. So for this, absolutely it will be O of n, because we are traversing all the nodes. So the time complexity will be exactly similar to the binary tree. Binary tree. So we just come up with some logic like we'll be dividing nodes and making this as a binary search algorithm. But we have some drawback, like we in some cases we will be constructing a skew tree. To avoid this only, we are going for AVL tree or red black tree. Okay, so these are the two trees that are basically having both the property like binary search tree and also a balanced binary search tree. Okay, so basically these names will be balanced binary search tree. So this is going to be the name of these two trees. Okay, now hope you understand why I am telling in the types of trees itself the binary search tree is not as much as efficient. Okay, it will be efficient in some cases, it will be inefficient in some cases, but in AVL and red black tree it will be always efficient. Okay, fine, let us see the code so that you can understand this clearly. I'll be taking the C++ code. If you want a Java or Python code, search in the description. Okay, now see here comes class node. For one node there will be three attributes. What are those? Value, left and right. Okay, now in the constructor just initialize them. So value will be the given parameter, given in the parameter. Meanwhile left and right will be a null pointer. Okay, now so this is the class that is going to be implementing the binary search tree. So here I will be taking a data member called root. Now I will be initializing the root in the constructor itself. So whichever element I am giving or whichever the value I am passing while creating the object is going to be the root value. Okay, now void insert. So this is going to be the function that is going to do a insertion of any element to the binary search tree. Okay, so here I will be getting two parameters. One is value, another one is root. Okay, fine. So if there is no the root is equal to null pointer, then I will be returning that itself. Okay, else what should I do? I'll be checking whether value is less than the root value. Then where should I go? I'll be going towards the left subtree. Can I understand this? When the value is less than the root value, then I am going and searching in the left subtree. First of all, I will be checking whether the root left is equal to null pointer. If it is so, there itself I will be inserting the new node. If not, I will be again going to its recursion recursion call. Okay, for insert value and root left, that like that. Can you understand this? Yes. Now else if value is greater than root value, then what should I do? I'll be going and checking whether my root right is equal to null pointer. Then I'll be making that particular node to the right child as a right child. Okay, else what will I do? I'll be going towards the right subtree. Can you understand this? So this is just a recursion call that will be going towards the left subtree or towards the right subtree. That's it. Okay, else I don't do anything, just return. So here you don't want to put this also. If you put this, it is okay. Okay, in my opinion, you don't want to put this also. Okay, fine. Now let us go to the search. So searching is quite different from the binary tree while comparing to the binary search tree, because in binary search tree we will be going with the use of its property. Okay, we are not doing any in order or pre order, post order or level order such thing. We are just going with the property. So see here, if root is null pointer, then return false. Okay, this is going to be the base condition. Now if the root value is equal to the value, then return true. This is also going to be the base condition. So there are two base conditions. Okay, now else if value is less than the root value, then what should I do? I'll be going towards the left subtree and checking for the particular value. Can you understand this? Okay, else what should I do? I'll be going towards the right subtree and checking for its value. Okay, so basically when the value is less than the root value, I'll be going to its left subtree, or I'll be going to the right subtree. If the value is equal to the root value, then just return true. That's it. Okay, so this is going to the search option. Okay, now for in order traversal I have written here, and pre-order and post-order traversal and level order traversal. But in particularly for binary search tree, we only needed the in order traversal. If you want, you may add all the other traversals also, but in order traversal will be mandatory for the binary search tree. Okay, now deletion. So deletion will be kind of something like you want to dry run by yourself. and you want to know about recursion in thorough manner so that you can understand the deletion of the node. Okay, so see here, let me go with this. So here also, if the root is equal to null pointer, then I will be returning a null pointer. That's it. Okay, or just return. Okay, now if value is less than root's value, then what should I do? I'll be going towards the left subtree. I'll be going towards the left subtree. In that case, I'll be making what? Root's left is equal to delete node of value comma root's left, which means for my left child, let me give this to the recursion call like that. Can you understand this? Which means for my left child, I'll be getting the result of the delete node of the left subtree and storing that like that. Okay, this is the way I told you. If you can understand the recursion, then only you can understand this code also. Okay, now else if value is greater than the root value, then what should I do? I will be making my right child as my node, this recursion call towards the right subtree. Okay, fine. Else means what is the meaning? Which means I am standing in the node that should be deleted, which means value is equal to the root's value. Can you understand this? At this particular point, I have three cases. One is no child, another one is one child, another one is two child. See here comes two child. Okay, so first let us finish the one child, sorry, no child. Okay, if there is no child, then it is case like we want to delete the leaf node. Okay, then we can directly delete that particular node, okay, and return the null pointer so that the previously called recursion call will be giving a result as null pointer. For example, see here, if I am having a node like 10 and its left subtree left child value is 7. Okay, now I want to delete 7. Then first I will be here. Okay, now I'll be checking whether 10 is equal to 7. No, 10 is less than greater than 7. Yes, then I will be going towards the left subtree. Now 7 is equal to 7. Then I want to delete it, right? So delete it, and I'll be returning back as null pointer, which means initially it will be like some address and 10, and here comes null. After returning the null pointer here, this will be again replaced as null. So now it will be like I have deleted its left child like that. Okay, so this is what I have done in these two lines. Okay, now if there is one child, it may be of either it don't have left child or it don't have right child, right? So that will be two cases. So first case is if it doesn't have any left child, then what should I do? I'll be taking the right child, and I'll be deleting the root, and I'll be returning its right child. Which means instead of the root, I'll be replacing it with right child. That's it. Same thing for the left child also. If there only exists left child, then I'll be doing this same thing there also with the left child. Okay. Now, if there are two children, then what should I do? I'll be taking the node which is minimum in my right subtree. I'll be taking a node which is minimum in my right subtree. So this line represents that. Okay, and just understand. Still, I didn't complete this functionality, right? In future, we will be completing this. Now, just understand. If I just calling this function, it will be returning my minimum value to. It will be returning the minimum value to the call. Okay. Now, root value will be my successor's value. So I replace the value. Okay. Now, root right is equal to delete node of successor value comma root right, which means from here you can understand. Now we are going to delete that particular node which is minimum in my right subtree. So this is going to be the recursion call again. Okay, until I don't have anything to delete. That's it. Okay. Now after this I will be returning the root. If these conditions are not satisfied, okay, then I will be just returning the root. Fine. Now comes the find minimum. So see here, in find minimum, I'll be starting from the root, and if I have root left, then I'll be going to its root left. Can you understand this? I'll be going to the leftmost node. I'll be going to the leftmost node whose left will be none. Whose left child is none. That's the reason why I'm going up to what? Root and root left. Can you understand this? And return the root after finishing the looping. Okay. Similarly, same thing for the maximum also. So now you understand the whole implementation, right? Now there is a small mistake, I think so. In insertion, okay, it will be fine. It will be fine. Okay, fine. That's it. Okay. Now in the main function, you can also do this by using the menu driven program. Okay, that's your wish. Now I hope you understand this entire implementation. If you have any doubts, then you can comment below, and if you found any mistakes, then also you can comment below. Okay. And if you really like this video and subscribe to my channel. Don't skip any videos in this playlist, because all videos will be helpful once you are going for a competitive programming, because this binary search tree will be more important when you are going for a competitive programming in LeetCode. And also if you are going for gate examination, there also they will be not asking about a code, but they will be asking about some properties in the binary search tree. Okay, and I hope so it will be more clear. And just see here one important point: in in-order traversal only we will be getting the sorted order. Always remember that for the binary search tree. Thank you.